Yeah, welcome. So the topic we'll be discussing in this lecture is forward and backward chaining. So in the last lecture, we have discussed about resolution. So resolution is an effective method of inference. Uh, the resolution technique is complete and sound. Sound in the sense whatever it infers that will be correct, and complete in the sense it can infer everything in the knowledge base. Um, but actually resolution is the time complexity of the resolution is quite high, and full power of the resolution is not required in most of the cases. Resolution is a powerful technique, and most of the cases it does not demand that much power. In in some of the real world knowledge bases, if we satisfy certain restrictions, what is these restrictions we will understand soon. In some of the real world knowledge bases, if we satisfy certain restrictions, then we can use more efficient inference algorithms provided these restrictions were satisfied. So here the point is, we are not saying that there is some algorithm which is much better than resolution. So resolution is applicable to resolution is applicable without any restrictions, right, to a particular problem. But say that in some knowledge bases, if they satisfy certain restrictions, if the given knowledge base satisfies certain restrictions, then we can have some efficient inference algorithms which are better than resolution. And such inference algorithms are forward and backward chaining, right? So the point here is we cannot use forward and backward chaining every time for all cases. Forward and backward chaining can be used only only if the knowledge base satisfies certain restrictions. If those restrictions were not satisfied, then obviously you have to go with resolution. But if those restrictions were satisfied, then we can go with some efficient inference algorithms, which is nothing but forward chaining and backward chaining. So this is the what do you call? This is the motivation behind this topic. So basically, why we are learning forward and backward chaining. Forward and backward chaining is also one type of inference mechanism. But already we have discussed a powerful inference mechanism, which is resolution, which is complete and sound. But its time complexity may be quite high, right? And the full power of resolution may not be required in all cases. Hence, and in some of the real world knowledge bases, if they satisfy certain restrictions, then we can go for some more efficient inference algorithms. And these efficiency comes into the picture only because of these restrictions. If these knowledge bases satisfies these restrictions, then these inference algorithms will become efficient than resolution. Okay. So what are those inference algorithms? They are nothing but forward chaining and backward chaining. But there is a condition to use forward chaining and backward chaining. They cannot be used in all cases. They can be used only if these restrictions were satisfied. Fine. Now, what are those restrictions? So there are two cases of restrictions which we are going to discuss. One is called as definite clause. The other one is called as horn clause. So we are going to discuss two cases of restrictions. One is called as definite clause. The other one is called as horn clause. So what is a definite clause? A definite clause is a disjunction of literals with exactly one positive literal. A definite clause is a disjunction of literals. That is it can have uh, it can have multiple literals, but all those literals should be connected with only disjunction. That is or. They should be connected only with or, and there should be only one positive literal. That is, remaining all literals should be negative. There can be any number of literals, and all the literals should be connected using disjunction, and also exactly there should be only one positive literal. Such a clause is called as definite clause, right? I guess you are following. So here this is an example for a definite clause. Not L11, not breeze, B11. All these are connected. These three literals were connected using disjunction. And you can see out of these three literals, two are negated and there is only one positive literal. Hence, it is a definite clause. Whereas this is not a definite clause. Here, all these literals were connected using disjunction. They are connected using or. But there are two positive literals. Hence, they are not. Hence, this is not a definite clause. Right? So, for example, if something like this A or not B or not C or D, this is a definite clause because it can have only, it should be, the literal should be connected using disjunction and there should be exactly one positive literal. Such a clause is called as definite clause, right? Okay. So this is one restricted form. Definite clause is one restricted form. The another restricted form is called as horn clause. What is a horn clause? A horn clause is also a disjunction of literals with at most one positive literal. A horn clause is also a disjunction of literals with at most one positive literal. See, the difference is in a definite clause, there should be exactly one positive literal. Whereas in a horn clause, it can have at most one positive literal, which means, for example, this is a horn clause, not A or not B or not C. This is a horn clause because here all are negative literals. There are no positive literals. Hence, this is a horn clause. It can have at most one positive literal. So, for example, not A or not B or C. This is also a horn clause, right? So, so minimum it can have 0 positive literals and maximum it can have one positive literal. Such a clause is called as a horn clause. So, for example, not A or B or C. This is not a horn clause. This is also not a definite clause because definite clause should have only one positive literal. Okay, whereas this has two positive literal, and a horn clause can have at most one positive literal. That is, it can horn clause can have 0 positive literal or what you call one positive literal. But this is not a horn clause, and also it is not a definite clause, right? Whereas this one, if you see, this is a definite clause and also a horn clause. This is a definite clause and also a horn clause, right? Whereas this, if you see, this is a horn clause, but this is not a definite clause. The first one, the example one is a horn clause, but it's not a definite clause, right? The example two is a horn clause and a definite clause. The example three, this is not a definite clause and also it's not a horn clause, right? Okay. So all definite clauses are horn clauses. So that is understandable. All definite clauses are also horn clauses, right? And also clauses with no positive literals are also horn clauses, right? Now clauses with no positive literals, they also have another name that is called as goal clauses. If a clause does not have any positive literal, then they are also called as goal clause. For example, if you have not A or not X or not P, here all are negative literals. There is no positive literals. So this is a goal clause. So you can call this as goal clause, or you can also call it as horn clause, right? Because horn clause is the one which contains at most one positive literal, right? So these are the restricted forms. These are the restricted forms which we are going to discuss in today's class. So yeah, so with this intro, let us get into the topic. So what we are going to discuss? So we are going to discuss forward chaining and backward chaining. Now the condition for applying forward chaining and backward chaining is, if you want to apply forward chaining or backward chaining, then all the clauses should be in definite clause. If for a particular problem, if all the clauses can be represented as definite clause or horn clause, then we can apply forward chaining or backward chaining, right? And why we are going for forward chaining and backward chaining when we have resolution in place? The reason is, if we are able to achieve forward chaining or backward chaining, then the problem can be solved in linear amount of time of the knowledge base. Then the problem can be solved in linear amount of time of knowledge base, which may not be possible with resolution. So that is the reason why we are interested in forward chaining and backward chaining. But the condition is we will be able to use forward chaining and backward chaining only if you are able to represent all the rules. Only if you are able to represent all the rules as a definite clause or as a Horn clause. I guess it's clear. So with this intro, let us get into right. So to summarize, we are in today's session we are going to discuss about forward chaining and backward chaining, which is also one type of inference. So the immediate question comes is, why do we discuss forward chaining and backward chaining when we have already learned resolution, which is a powerful inference technique? Yes, no doubt that resolution is a powerful inference technique. It is sound and also it is complete, but its time complexity is quite high. Hence, we have another alternative called forward chaining and backward chaining. But we can use forward chaining and backward chaining if certain restricted cases or if we have certain restriction conditions that are satisfied. What are those restricted conditions? Those restricted conditions are definite clause or Horn clause. So for a given problem, if all the rules can be represented as a definite clause or a Horn clause, right, then we can apply forward chaining or backward chaining. Why we are applying forward chaining or backward chaining? Because if you apply forward chaining or backward chaining, then the problem can be solved in linear amount of time of the knowledge base, right? So with this intro, let us get into the actual concept of forward chaining and backward chaining, right? Okay, fine. So this we have already discussed. The what is Horn clause? We have a Horn clause can have at most one positive literal. So this is an example for a Horn clause, not P, not Q or V. This is a Horn clause, right? And this is also a Horn clause, not P or not W. But this is not a Horn clause because here there are two positive literals. And what's a definite clause? It has exactly one positive literal, right? Okay. Now, if something is in a definite clause, so if something is in a definite clause, then that can be represented in a different way. For example, consider this: negation of C or negation of B or A. Negation of C or negation of B or A. So this is an example for a definite clause. Now this can be written like this: C conjunction B implies A. Is that clear? So if there is a rule or if there is a statement which is represented in definite clause, then that can be represented like this, right? So for example, here we have not P or not Q or V. This can be represented as P and Q implies V, right? So this is very important. This rule is important. So because of this rule only, we are interested. Because of this representation only, we are interested in definite clauses. So if something is in the definite clause, immediately we can represent it in this way. Okay. If we represent it in this way, then what is our advantage? If we are able to represent something in this format, then what is our advantage? The advantage is that then we can easily apply modus ponens and we can prove that. Because you know that what is modus ponens states that if alpha implies beta is a rule, and if you know that alpha is true, if alpha is true, then we can infer that beta is also true. Similarly, if you have something of this form, C and B implies A, and if you know that C and B is true, then you can infer that A is true, right? So this is the reason. So our inference will become easier. So that is the reason why we want to convert the representation in definite clause to this particular format. Okay, fine. So if something is in the Horn clause or in, so this is also a Horn clause, right? All definite clause is also a Horn clause. So then we can represent something like this. So that's what this is the generic version, right? Okay. So this is the algorithm for forward chaining. Let us first discuss the example, then we will come to the algorithm so that things will be clear. So first let us discuss this example. So here is an example. Here, see, these are rules. These are rules. This is, say, this is one rule. We'll call it as a, or I will start number from here. So this is rule 1. This is one rule. This is rule 2. This is rule 3. This is rule 4. This is rule 5. Okay. This you can say as rule and also fact. This is a fact. This is a truth we know. This is, we can say this is truth 1. This is truth 2. Okay. Right. So here what we want to prove, in the sense, here we want to prove that Q is true. Here we want to prove that Q is true. Q is true. This is what we want to prove. Right now, how are we going to prove that? We are going to prove that. We are going to prove that using forward chaining technique. Right? We are going to prove this using forward chaining technique. For this, we are going to use AND OR graph. So if you recall, previously we have discussed AND OR graph. So that we are going to use here again, AND OR graph. So this entire thing, whatever all the rules and truth were here, these rules and truth, we are representing it as AND OR graph. Right? So let us start with the basic truth. What are the basic truth? We have A and B. A, B, right? So from A and B, we can infer what? L. So this A and B, here L comes, right? So this A and B are the basic truth. And from this, we are inferring this L, right? Okay, so that is how this diagram comes. So A and B, this arc, there is an arc which connects A and B, which represents it is AND. Okay, which represents it is AND. If A and B are true, then L is true. Okay, right? Similarly, B and L, or let us, yeah, B and L implies M. So this B and L. So here also there is arc. If both B and L are true, then M is true. Okay. Similarly, L and M implies P. If L and M are true, then we can infer P. Okay. Similarly, then A and P. So this is A, this is P. P we are taking from here. If A and P are true, so that is connected using this arc, then we can infer L. Okay, then also, so there are two ways of inferring L, either through A and P or through A and B, right? And if you know that P is true, so with L and M we can infer P. If you know that P is true, then from P we can infer Q. So this is what this diagram is about. Now, how we are, so this is just here I'm not explaining the diagram. We are not yet into forward chaining. So how the forward chaining works, that's we'll discuss. So for forward chaining, initially there will be a queue. This queue will be initially empty. Okay, this queue will be initially empty. First, what we'll be doing in this sense, we'll be adding one by one truth. So here, what are the truth? All these are rules. Only we have two truths, A and B. So A and B are the truth. So we will be adding one by one truth to this queue. So first truth, say let us add A, and you add A here, right? You add A here. Okay, but before that, okay, the A is added to the queue. Let us hold on. Let us hold on here. But before that, one more thing we should do. For all these rules, we have to work out something. If, say, take this rule, rule 1, A and B implies L. So this A and B implies L. In this rule, if you see, this A and B is called premise. The left side part is called as premise. The right side is called as conclusion, right? So for every rule, there is a left part and a right part. The left part is called as premise and the right part is called as conclusion. So for every conclusion, you have to find like how many premise it has. So this conclusion, this one, it has two premise. This one, it has two premise. This also, it has two premise. This also, it has two premise. This, it has only one premise. Right? This info, every conclusion, it has how many premise. This info should be updated in this AND OR graph. Right? Okay. So let us take A and B implies L. A and B implies L. So this implies L. This has how many premise? Two premise. So I'm adding 2 here because this is the connecting point. So here we are adding that 2. We are representing as 2. Okay, because this L conclusion, it depends on two premises. Okay. Similarly, A and P implies L. A and P implies L. So this junction, this conjunction, right? Here also via this path also there are two premises. Okay. Then B and L implies M. This is B and L implies M. Here also there are two premises, right? Then L and M implies P. This L and M implies P. So here also there is two premises. Then P implies Q. So P implies Q. Here there is only one premise, right? So this info we will update before starting with that Q. This info should be updated in the graph. Now we'll start with the Q. So in the Q, first we will add one by one facts. So we currently have only two facts, A and B. So we'll add A, which means we are going to explore A. So whichever the node we are going to explore, that I'm going to route it. So we are going to explore A, right? So when you explore A, here in all the rules you see, in whichever the rules where A comes at the premise. So one is in this rule A comes at the premise, and in this rule A comes at the premise. So wherever A is coming at the premise, you should reduce this number. Okay, because we are exploring it, because we know that A is true. A is true. So it means that that premise is satisfied. So here why we are adding this number represents that to prove that L is true, we have to satisfy two premise. Similarly, for rule 2, to prove that L is true, we have to satisfy two premise. Similarly, to satisfy M is true, we have to prove that M is true, we have to satisfy two premise, so on and so forth. Now we know that A is true and A is added to the Q. Hence, and A is connected with which rules? Rule 1 and rule 2. So for these two rules, we will decrement the number of premises to be satisfied. So this will become 1. This will also become 1. So that change we will reflect in the graph also. So here this 2, this A and B, this 2 becomes 1. Because we know that A is true now, as it is, as we added to the Q. So only the time at which it is added to the Q, we are making these changes, right? And A and L, A and P implies L. Out of that, we know that A is true. So this also will become 1, right? Okay, fine. Now what should we do? Now A we have explored, but still nothing has become 0. Nothing has become 0. Our objective is to make everything 0. Our objective is to make everything 0. Then only we can prove that Q is true. So let us add the second fact. A we have already added. Let us add the second fact B. Now when you add B, now we are going to explore B, right? So when you explore B, again you see where B is coming at the premise. B is coming at the premise here and here. So here now already it is 1, it will become 0. And here this 2 will become 1. Okay. So this B and A implies L, that will become 0. This path becomes 0, right? And there is another one which is, sorry, B and A implies L, that becomes 0. And another one is B and L implies M. Okay, L is not yet explored, so this will become 1. This will become 1. Okay. Now we know that A is true, B is true, and this A and B is true. We know that A and B is true, and this arc has already become 0, which means L is true. Which means L is true. So now we came to know that L is also true. So this is the third truth we come to know, right? So now we will add this new truth to the Q. So what is the truth we are going to add? L we are going to add to the Q. Okay. After adding L, now explore L. Now explore L. So when you explore L, again you see where L is coming in the premise. So L is coming in R3 and in R4. So for those places, we will reduce this number. So this will become 0 and this will become 1. So B and L, okay, B and L implies M. Already B is truth we know, L is truth we know. So B and L will obviously be true. So this will become 0, right? And L and M, L and M implies P. So we know that L is true. So this will become 1. Okay, fine. So now one more 0 we got. So we know that now M is true. Now we know that M is true. So now we are going to explore M. Now we are going to explore M. So add M to the Q. So when you explore M, again you check where M is coming at the premise. So M is coming here, only here it is coming, right? So this will become what? 0. This will become 0. So already L is truth, we know. Now we know that M is also truth. So L and M implies P. So this path is now cleared. This path becomes 0, right? So 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 as L and M becomes 0, as L and M is true, we know that P is true, right? So 0 means there is nothing to prove because both the premises were satisfied. That is what 0 represents. Okay. So now we know that P is true. So we will round off P, which means we'll add P to the Q. So add P to the Q. Now explore P. So again, now you see where P is coming at the premise. So P is coming here and also P is coming here. So wherever P is coming, we will decrement it by 1. So here it becomes 0 and here also it becomes 0, right? So this P and L, P and A, right? P and A implies L. So that becomes 0 already, but L is added. Now P implies Q. This also becomes 0 because already P is true. So Q is also true. Hence, we have proved that Q is true. Okay. So now Q can be added, right? So this is how this forward chaining works, right? But if you want to apply forward chaining, all the rules should be in definite form or it should be in Horn form. Okay, all the rules should be represented as a definite clause or as a Horn clause, right? So I guess you understood. So that is what it is explained, these different slides. So first it is numbering. Okay, then exploring the nodes. So first we know that A and B are true, then start exploring. When you explore, you keep decrementing, right? So previously these 2 points were 2. Okay, so when you first we are exploring only A. So you can see that inside a red is added. So only these two things becomes 1 1, right? Then when you add B also, this becomes 0, right? So on and so forth, it continues. So we repeat this process until everything becomes 0. And hence finally we prove Q, right? So this is how forward chaining works. Okay, fine, right? So now we'll be discussing about backward chaining. See, as you can see in forward chaining, we move with the truth. First we start with the truth and from the truth we move on to the goal. Our goal is to prove what Q is true. That is what we want to prove. So, but how we started? We started with A and B in forward chaining. We started with the basic truth we know, and from that we infer further facts and so on and so forth. We finally prove the truth. Whereas for backward chaining, we start with the goal state. What is our goal state? Q is true. Okay. So Q is true. It is not yet proven, so that it is represented in green color. Whichever is not proven, that is represented in green color. Whichever is proven or whichever is a fact, that is represented in red color. This red circle represents fact or truth. Okay, red circled with a red background. Okay, whereas this green circle represents it is yet to be proven. So we want to prove Q is true, but with backward chaining. If you want to prove Q is true, then first you should prove P as true. Okay, so P also we are circling, because to prove Q as true, we have to first prove P as true. If we want to prove P as true, then we have to prove L and M as true. Okay, so we are circling L and M, right? So this shaded means this means first we are starting with Q. We want to prove Q as true, but if you want to prove Q as true, then P should be proven. So to prove Q, P should be proven. So that is what P, that it means Q depends on P. That's what it means. Similarly, if you want to prove P as true, then L and M should be proven. Okay. If you want to prove L, then if you want to prove L, then A and P should be proven. A is a fact that we know. Okay, A is a fact that we know. But what about P? P we don't know. Okay. So we are circling A also as green and P also as green. A is a fact we know, but L cannot be derived until you confirm that P is true. So that still this is also green, right? Okay. But there is another way to prove L, that is by A and B. So along the path of A and B, we can prove L. Now there is no green around A, you can see, because A is true, we know, B is also true, we know. So we can prove L, right? So with this path, now we can make L as red, because if A and B are true, then L should be true. Okay. Hence we made L as red. Okay. Right. If L is true and B is true, then we can prove M. Right. So from L and B, we can prove M. Right. Okay. From L and M, we can prove P. From L and M, we can prove P. Okay. And from P, we can prove Q. So this is how backward chaining works. So in backward chaining, first we start with the goal and then we backtrack or we do some recursive kind of thing and hence we prove, right? So forward chaining is mainly used for data driven applications like object recognition or routine decision, something like that. And backward chaining or appropriate for problem solving, like where is the home, what is the result of equation, so on and so forth. Right. Now let us discuss the algorithm. So with this knowledge, now we can understand the algorithm for forward chaining, which we have initially left out. Okay. So this is the algorithm. So this is knowledge base. So knowledge base is nothing but all these rules. These rules are the knowledge base. Okay. Not only rules and facts, everything is available in this knowledge base, right? So this algorithm takes this knowledge base as input, and what it want to prove, it want to prove Q. It want to prove that Q is true, right? Count is equal to a table. Count of C is the number of symbols in C's premise, right? Count of C is the number of symbols in C's premise, which means we have many clauses. C represent clauses. We have many clauses, right? Each of these is clause. Each of these is a clause. P implies Q is a clause. L implies M is a clause. Sorry, L and M implies P is a clause. B and L implies M is a clause. So basically all these are clauses, right? So how we started initially, for this class how many premise, for this class how many premise, for this class how many premise, that is how we started, right? So that is what this count contains. So count is basically an array. Count of C contains number of symbols in C's premise, right? That is number of literals in a particular class premise. So if you have 10 clauses, then C of 1 will have number of premise in the first clause. C of 2 will have number of symbols in the second clause. Number of symbols in the second clause is premise, right? C of 1 contains number of symbols in the second clauses in the first clause premise. C of 3 will contain number of symbols in the premise of the third clause, so on and so forth, right? Okay. Inferred. Inferred is equal to a table which is initially false for all S. What is all S? All S means all symbols. For all symbols, it is initially false. Okay, because initially we have not proven anything. So initially we don't know. So if you consider this whatever we have discussed here, initially we don't know whether L is true or not, whether M is true or not. All those things we don't know. So initially, what is our assumption? Initially we assume that L is false, M is false, everything is false. Okay. Initially we assume that L is false, M is false, P is false, Q is false, right? So that is what this statement says. Inferred equal to table inferred of F initially false for all S, right? Agenda. What is agenda? Agenda is equal to a queue of symbols. It is the queue. It is the queue, right? It is the queue initialized with symbols that are true. And this queue initially what it contains? It contains the symbols that are true. So in our case, what are the symbols that are true? These symbols we don't know. What is P? We don't know. So we assume it is false only. Q also we assume as false. All these symbols we assume as false, except A and B. Only A and B we assume as true, because this is a fact given. So this Q will initially contain only the symbols that are true. So it will hold A and B. So in the explanation, I said first A, then B, but also you can assume already it contains A and B, right? Now get into the algorithm. So this Q is called as agenda. This Q is, we are naming this Q as agenda. Okay. While agenda is not empty. So if this Q is not empty, what we have to do? P is equal to pop of agenda. Remove one element from agenda. So P is equal to pop means it will remove the first element from the Q. So A will be removed. So P is equal to A, right? If P is equal to Q, Q is the goal state. Q is the one we want to prove. Is P is equal to Q? No, P is not equal to Q. P is equal to A. If P is equal to Q, then return true. It means we have proven. But no, in our case, P is not Q. Hence, come to the next statement. If inferred of P is equal to false, inferred of P, in our case, it is not false, it is true. For all other symbols, it is false. But A and B, it is not false. A and B, it is true. Right? So in our case, what are the symbols? If you see, these are the symbols Q, P, L, M, A, and B. Q, P, L, M, all these initially it will be set as false because we don't know what is whether they are true or not. But A and B are true, right? Because they are fact. So here that's what we are checking. If inferred of P is equal to false, inferred of P contains A is true. So so it is not false, right? If inferred of P is equal to false, then make it true. Okay, see this, what does it mean? Means if inferred of P is equal to false, then make it true, right? Okay, sorry, see let us understand it little different way, okay, for this algorithm sake, right? See, inferred, what is inferred? Inferred is a table, inferred is a table which is initially false for all s, that is it is false for all symbols. So what are the symbols in our case? In our case, these are the symbols Q, P, L, M, A, B. Everything is false, including A and B. Okay. Q, P, L, M, A, B. Okay. Q, P, L, M, A, B. All these will be initially false in inferred. In inferred. Okay. So in inferred of Q will be false, inferred of P will be false, inferred of L will be false, inferred of M will be false, A will be false, B will be false. Everything is false. Right? That's it. Agenda is a queue of symbols which is initialized with the symbols that are true. Okay. But agenda contains the symbols that are true. Which symbols are true? A and B are true. So A and B alone will be in agenda. But in inferred table, everything will be false. Right? Okay. Why? Because that is how our algorithm flow will become understandable. Now, while agenda is not empty, P is equal to pop of agenda. So P is equal to A is removed from here. If P is equal to Q, P is not equal to Q, so we won't return true. If inferred of P is false, inferred of P, what is inferred of? Inferred of, in inferred everything is false, right? So inferred of P, A is also false. Then what we do, inferred of P is equal to true. So inferred means, actually inferred means whether it is explored or not. That is what it is meaning. Okay. So the meaning of inferred is whether that particular node is explored or not. Initially nothing is explored, hence it is false, right? Whereas agenda contains the nodes which are true or which are fact, the symbols which are true or facts, right? Please understand that way. Inferred means whether the particular node is explored or not. Okay. So initially nothing is explored, even A is not explored. So inferred of P is false. So inferred of P is equal to A, which means A is false. Then what we make, inferred of P is equal to true. So we make inferred of P as true. That is inferred in our case, it is A. So we are going to explore A. We are going to now explore A. Now it is no more in the inferred list. Okay, this is the inferred list. Now A is not in the inferred list. Okay, we are making it true. Then what we do, for each class in C, for each class C in KB, for each class C in KB that contains P in premise, See, this is interesting. This is for each clause C in KB that contains P in premise, decrement count of C. So what does it mean? For how many classes we have? In our case, these are the classes. All these are classes. This is, we can say that this is for each clause. So we can say that this is clause 1. We can say that this is clause 1, this is clause 2, this is clause 3, this is clause 4, this is clause 5, right? For each class in KB that contains P in premise. What is P? P is A, which that contains P in premise. Okay. Wherever A is there, what we want to do? Decrement the count. Decrement the count. Initially, what is the count? Count is the number of premise, number of symbols in the premise. Initially, this is 1, this is 2, this is 2, this is 2, this is 2. Now, for all these clauses, you have to check. Wherever A is there in premise, decrement it by 1. So this will become 1 and this will become 1. That's what it says. Okay. If count of C is equal to 0, then add C dot conclusion to agenda. Then you check for any of this class, is the count has become 0? No, still it has not become 0. If it has become 0, then add this conclusion to agenda. Right? Currently our agenda contains only A and B. Otherwise, repeat this process. Now in our case, it is not what you call, it is not nothing is 0. So once again go. Then once again go. P is equal to pop of agenda. So now it will take B, right? Again it checks if P is equal to Q. Then no, P is not Q. If inferred of P is false, yes, initially it is false. Then inferred of P is equal to true. It is inferred of B now becomes true. So B is, now we are going to explore B. For each clause C in KB, now for each clause C in KB that contains P, now P is B. So wherever B is there, decrement count. So wherever B is there, now decrement count. So B is here, so this will become 0, right? B is here, so this will become 1, right? Okay, wherever B is there, decrement the count. And then check if count of C is equal to 0, add C dot conclusion to agenda. So is for any count it is 0? Yes. For this, for any clause, for this clause it is 0. So add the conclusion to agenda. What is the conclusion? L. So add L to agenda. So L will be added to the agenda. Okay. Now again the loop continues. Now P is equal to pop of agenda. Now this will be L. Now inferred of L. This inferred of L is false. So now again we make inferred of L is equal to true, right? So on and so forth it continues. Now wherever L is there, decrement by 1. Wherever in the premise L is there, decrement by 1. So this will become 0 and this will become 1. Okay, this will become 0 and this will become 1. And again check if count of C is 0, then add C dot conclusion to agenda. So now M will be added to agenda. Now M will be added to agenda. Okay. So L is already removed. Now M is added to agenda. Right. Now in the next round, we take M. We check whether inferred of M is false. Yes, initially it is false. Now make it true. We are going to explore M. Now this for loop, what it do? Wherever for each clause C in KB that contains P. Now P is M. That contains M in premise decrement count. So wherever M is there in the premise decrement count. So here is M. So decrement count, this becomes 0. Right. So now something has become 0. So add C dot conclusion to agenda. So what is now? P will be added to the agenda. So M is already removed. Now P is added to the agenda. Now again pop of agenda. So we'll get P, right? This P is now removed. Is inferred of P is true? Is false? Yes, initially it is false. Now make it true. That is, we are going to explore P, right? Now wherever P is in the premise, decrement it by 0. Decrement it by 1. So here P is in the premise. So this becomes 0 and this also becomes 0. Right. So now we can add both L and Q to the agenda. L is already added and checked. So we need not add L. So now we can add Q to the agenda. Okay. Now pop Q. So Q is popped. Then check if P is equal to Q. Yes, P is equal to Q, return true. Right. So this algorithm will say that Q is satisfiable. Right. Sometimes if you go through all these things, but if you are unable to prove that P is Q, then P is equal to Q, then finally it will return false, which means this statement Q is true is not correct. Okay, so that's it about forward chaining and backward chaining. I guess you have understood. So let us stop here for today's session. Thank you.